introduction. Vector calculus focuses on the study of vector field along the curve and over the regions. It provides useful tools for analyzing physical quantities such as work done by a force, circulation, and rotation effect. Line integrals and Green's theorem allow this quantity to be evaluated efficiently. In particular, Green's theorem simplifies calculation by relating a line integral around a closed curve to a double integral over the enclosed area. Because of this, it is widely used in physics and engineering, especially in fluid dynamics and electromagnetism. Green's theorem was introduced by George Green in 1828. It described the relationship between the circulation of a vector field around a closed curve and the area enclosed by the curve. Consider a two-dimensional vector field given by F equals to Pi plus Qj. According to the Green's theorem, the line integral of this vector field taken around a positively oriented closed curve C is equal to a double integral over the region R enclosed by the curve. This result allows circulation to be calculated using area integration instead of evaluating the line integral directly. Here, C represents the closed boundary of the region, while R represents the area inside of the boundary. Green's theorem is useful because it simplifies calculation involving circulation and rotation behavior in vector fields.
Assalamualaikum and hi. My name is Atika Sharafana binti Ismail and I will continue with line integral. Line integral has developed in the early 19th century by Augustine Louis Cauchy and George Gabriel Stokes while they are studying fluid flow, electromagnetism, and variable forces. There are two types of line integral, which are scalar field and vector field. For scalar, it integrates a scalar field over a curve. The formula is given. For vector, it integrates a vector field along a curve, or we call it dot product. The formula is given. There are so many applications of line integral. For example, work done by a force, mass of a variable density wire, fluid flow or circulation, engineering of design, and others.
So I will be explaining question 1, which is we will determine the circulation of a two-dimensional force field using Green's theorem. We are given a force field acting on a narrow horizontal surface, which may represent water flowing across a shallow basin or air moving over a flat structure panel. Understanding the circulation of this force field is important as it has predict rotation motion that may cause material stress, erosion, and inefficiencies in engineering designs. The force field is given as F equals x squared yi minus y squared g. The region we are working on is bounded by two curves. The lower curve is y equals to x squared and the upper curve is y equals 2 minus x squared. These two curves meet and form a closed region, so Green's theorem can be applied. First, we identify P and Q by comparing with the standard form F equals Pi plus Qg. We get P equals x squared y and Q equals y squared. Now, we find the intersection points of the curve. We equate x squared equals 2 minus x squared. This gives 2x squared equals 2, so x equals plus or minus 1. Substituting back, we get y equals 1. So the intersection points are negative 1, 1 and 1, 1. Now we apply Green's theorems. According to the Green's theorem, the line integral around the closed curve is equal to the double integral of partial q over partial x minus partial p over partial y. First, we differentiate q with respect to x, which gives 0. Then we differentiate p with respect to y, which is give x squared. So the integral becomes negative x squared. Now we set up the double integral. The limit of x are from negative 1 to 1 and the limits for y are from x squared to 2 minus x squared. So the integral becomes negative integral from minus 1 to 1, integral from x squared to 2 minus x squared of x squared dy dx. We integrate with respect to y first, then x. After simplifying and evaluating the limits, we get the final answer. The circulation of the force field around the closed region is negative 8 over 15.
For the method calculation, we start the method comma with restart and with vector calculus, then the with plots, then we use the plot based on the x squared and 2 minus x squared. So next we use the plot and the equations and to find the region C bounded by y equal to x squared and y equal to 2 minus x squared. For the method calculation, next we use the p equal to x squared multiplied with y and q equal to negative y squared. Next common is integrand equal to differentiate qx minus differentiate py. Next is simplify the integrand and we got the answer is negative 8 over 50. Next, we use the p equal to x.
Next, I will continue with question 2, which is compute the total radiant energy absorbed by the antenna along one full helical turn by evaluating the line integral E equal to f of x, y, z respect to s, where ds is the differential arc length along C given the y path is modeled by vector rt equal to 3 cos t, 3 sin t, t is from 0 until 2 pi. And the electromagnetic radiation intensity, or we call it energy per unit length, at any point along the antenna depends on the horizontal orientation and is given by the scalar field f of xyz equal to x squared plus 2y. For solution, step 1 is to find the ds. So the vector rt is given, so we have to differentiate the vector rt to get r prime t, and then we have to magnitude it, magnitude r prime t, as ds is equal to magnitude r prime t dt. So we will get ds equal to certain dt. For step 2, we have to express the f of x, y, z. We can list out the x, y, and z value from vector rt, which we will get x equal to 3 cos t, y equal to 3 sin t, and z equal to t. Then we just have to put the value into f x, y, z equation, which is equal to x squared plus 2y. Then we will get f x, y, z equal to 9 cos squared t plus 6 sin t. For step 3, we have to set up the integral. It is given that e equal to integration of f of x, y, z respect to s. So we just have to put the value that we got from step 1 and step 2 into the equation, and we will get the e is equal to certain integration of 9 cos squared t plus 6 sin t respect to t from 0 till 2 pi. For the last step, we have to evaluate the integrals. Since e is equal to certain integration of 9 cos squared t plus 6 sin t respect to t from 0 till 2 pi, we can calculate the integration separately. Firstly, we can calculate the integration of 9 cos squared t respect to t from 0 till 2 pi. We will get the answer is equal to 9 pi. Then we will calculate the integration of 6 sin t respect to t from 0 till 2 pi. We will get the answer which is equal to 0. Therefore, we can substitute the answer into the e equation. We will get certain multiplied with 9 pi plus 0. Then we'll get the final answer, which is e equal to 9 pi certain. That's all from me. Thank you.
For the mapper calculation, we start with restart command that used to clear all previously defined variable in mapper. Then we use the command with vector calculus and with plots. And after that, the parametric vector function is defined as rt, 3 cos t, 3 sin t, and t. That is represented as 3-dimensional helix. And then the plot 3D command is then used to visualize the helix. Parametric vector function is defined as rt equal to 3 cos t, 3 sin t, and t. Next, the differential arc length is computed. By differentiate the position vector and finding its magnitude, mapper shows that ds equal to square root 10. And this means the speed along the curve is constant. A scalar field is then defined as p x, y, z equal to x squared plus 2y. To evaluate the line integral, the parametric equation of the curve are substituted into the scalar field. This gives p rt equal to 9 cos squared t plus 6 sin t. Finally, the scalar line integral along the curve is calculated using the mapper, and then the mapper evaluates the integral, and the final result is 9 square root 10 pi. Parametric